back to class. Unfortunately, I don't have your quizzes to hand back right now. I will have them probably by 2:30 up in my office. I've got to go and take care of them. To go over that one. I looked at them as they were coming in, and I'm going to say just an estimate, probably 55–60% of you really knew what to do, but there's others that didn't seem to have a handle on this stuff, and it started to concern me that was, I thought, an extremely easy problem, but not knowing how to do it, maybe a lot of concern that people, I guess you had another test, so I can understand that you would say that it was more important to study for the other test. But these are gifts that I'm giving you on Friday. These are very easy problems. They're not like the test problems. They'll be more difficult to use. I mean, they'll be similar, but these are just bang, bang. If you did the homework, you got it, kind of deal. So I want to go through this. The problem is this. I had a resistor, and I had a resistor and a capacitor. And this fed an op-amp. This is negative, this is positive, this is grounded, and this is the output. The output was taken with respect to ground. This is Vn. On this one, R, these values really don't matter. I put them in there so you had values to work with, but they're trivial. Doesn't matter what they're. For R, I believe this was 100K, right? 100K ohms. And C was 1 microfarad. Can everybody see this? We can get it darker more. Now, for this problem, it didn't matter if you started and say that's ground, that's 0 volts, the current here is Vn over R. All that current goes through these two, right? The impedance of that is R, the impedance of that is 1 over Cs, right? You could go through the whole 9 yards and do it that way. Matter of fact, let me make sure I put the impedance of this as 1 over Cs, because this was a loss problem. Could have done it this way, but I noticed a lot of the people knew right away that when I looked at the transfer function, h of s, as V out of S over V in of S, what they immediately did is say it was minus Z2 over Z1. We developed this before, so they just did this. They just identified this as Z2, and I identified this as Z1. Right off the bat. Follow me? Let me see what I'm doing right here. How many remember that? Really? I mean, how many remember it? Be honest with me. We put this on the board, we worked this. You actually had problem after problem that used this, right? Honest, you guys remember this stuff? This was very straightforward. So now Z2 is the only thing you really had to identify. Z1 is just R. Z2 is what? It's 1 over what? 1 over R plus SC, correct? Yeah. Now I want to get S with just the coefficient of 1, so I divide by C. Follow me? So I divide top and bottom by C. Therefore, that's Z2, correct, class? Y'all see that right there? You can write the equations and get it very quick. It's a no-brainer. Now, if you see this as Z2, over here, this is equal to minus Z2, or minus 1 over C times the quantity 1 over S plus 1 over RC, right? And then it's divided by Z1. Z1 is R, right? So it's divided by R. And that is the transfer function. Y'all agree with that? That's the transfer function. Now, that was the first part, right? Get the transfer function in terms of the actual values in S, right? RC was what? This is what? 100K, right? 100K is 10 to the 5th. 1 microfarad is 10 to the minus 6, right? Therefore, RC is 1/10. Do you agree with that? Therefore, this is really going to be minus 10 times the quantity, 1 over S plus 10. Agree? How many see this right here? Right? Some people forgot the negatives. Yeah, we forgot to.
Why is it there?
What?
Why is it there?
Remember this, that if this current comes in here, I'm going to do this real quick. Please don't write anything, just listen to me. What's the current here? Vn, right? Divided by R, correct? How much of that current goes in the negative terminal? None. All comes up here, right? If all that current comes up here, isn't that going to cause a voltage drop plus to minus Z2 times that I? Right? It's just Z2, which is the parallel combination of those two, times this current, Vn over R, right? Do you see that? All right, now what's the output voltage? Start at the negative terminal, come here. That's 0, that's 0. This is going to go from plus to minus, or it is a drop. Therefore, the output voltage is minus that current times the impedance, right? Z2. You all see that? You forgot the minus signs. You're fatigued. You have absolution. Just don't make it happen. You want to follow me that minus sign right there? That was, I guess people made that mistake. Brian made a mistake. But otherwise, this is a trivial problem. I think we did, I'm not sure if we did exactly this values, but we did this problem. I know this. Do you remember this thing right here? Yeah. So that's H of S, which is H of S, therefore, is minus 10 divided by S plus 10. And therefore, H of T is going to be minus 10 times what? People, by looking. You got to know this one, right? E to the minus 10t U of T. And that was it. And that was a gimme. All right? Very easy problem. If you're not getting this like clockwork, then I know the test was there, but please do the homework I gave you anyway, so you're on top of this. This was a gimme. This was the easiest, I think, the easiest quiz I gave. All right, pretty much so. All right, that was the quiz. Now on to bigger and better things. Yes, sir?
Can you explain you got Z2 is equal to 1 over...
All right, let me show you what I'm doing. If you don't understand that, I'll just show you. When you talk about Z2, really we have two things in parallel, right? I can multiply this times this and divide it by this plus this, right? Or I could take 1 over the first impedance plus 1 over the second piece. So really that's what I'm doing. I'm saying Z2 is 1 over the first impedance, which is R, plus 1 over the second impedance. The second impedance is already 1 over CS, so it just becomes SC. 1 over CS is just CS, right? And it's very easy and very straightforward. There's no mystery in this one. It's a very, just like basic circuits, honestly. But you got to keep up with it. All right, class? Now, what I can tell you is, what I might do is put something like this. That should be a logical thing that you see me asking. Add one more item. I could do that. I could put an inductor in series with that instead of a resistor in parallel capacitor. But you have to sort of anticipate those type of questions. They're very obvious extensions of what we've done here. Do you follow me now? And if I put these two, capacitor and resistor in parallel there, then what? Z1 would be the parallel combination of those two, wouldn't it? And you would go forth with that information. Yes?
Same as Z2 over...
Well, I didn't put the values in here, but yes, it's 1 over R, 1 over R, whatever that R is, plus S times whatever that C is. Okay? You have a question back there? You look puzzled. I want to make sure I didn't say something confused. Okay. I put some homework up there. Did you get it? All right. Did you have any questions about the homework? Right.
Who ended up?
What? Do you have one? What's that? All right, which one was it? You need specs. Just tell me what it says.
Still loading. It's still loading.
Anybody got to tell me it's 25? I have it. I would rather have it here from you than looking at it. Do you have it?
Just find the single-sided Fourier series of the following transform.
Of what?
It's a trapezoid. So, I mean, I can show you it on my laptop.
No. Look at it. This is probably 25. Is it
No,
12?
there's no number.
What?
Yeah. It's just a feature.
It's just a rate.
Variables.
All right. Give me the variables, but help me. This is going to be the waveform. It's periodic, correct? All right, this is t. I'm going to call this x of t. At 0, at t equals 0, what's the value?
0 goes to a over a period of tau.
Is this tau?
Tau sub r.
Tau, oh, tau rising goes up?
Yes.
All right.
Stays flat until time tau.
Is this a?
Yes.
Okay. This is tau,
Yes, and then it descends another period of tau sub r.
and this is going to be tau plus tau sub r?
Yes.
And then it repeats, is this period t and it just repeats capital T?
Yeah.
Like so?
Mhm.
All right, now looking at that one, x of t, I'm going to ask you this. Didn't we do this? We did a problem almost identical, not quite because this has not got a 0 value for C0. But we did almost an identical problem, didn't we? All right, so we know x of t here can be represented by the Fourier series. Let me just put one period here. I know that for a fact that x of t here can be represented as the Fourier series, don't need to write this down, of c of n e to the j n omega naught t. And I know c of n is 1 over t, the integral from 0 to t, x of t times e to the minus j n omega naught t dt. I know that, right? Right there, correct, class? Now, what am I going to do? Am I going to bother doing this integral right here, class? That would be foolishness. You could do it, but it would be foolishness. I'm going to do one thing right off the bat. I'm going to get C0. C0 is 1 over t, the integral from 0 to t of x of t dt. The reason I'm doing that is something you have to get from the original waveform. You can't get it from the derivative values. So we're going to get our value for C0. Now by inspection, just looking at that, I said it was the average value between 0 and cap t before, right? Just look at that and tell me what it is. What is C0? Well, isn't that just a rectangle right there here? Right? So what is that? This has a width of tau. Think about it, right? I mean, if you think about this, isn't this, I'm sorry, is this tau right here in your book? Or is that tau, or is tau right here?
Tau is, before the, right there.
All right, if that's tau, you gotta be a little more careful. Because now the width from here to here is actually tau minus tau rise, isn't it? Times a. So I can say C0 would be equal to 1 over t times a times tau minus tau rise, right? Plus what? Plus a times what? Well, this is 1/2 tau rise a. This is 1/2 tau rise a. Or it's simply tau rise times a. Isn't it, class? Those two parts. So it's plus a times tau rise. Do you agree with me, class? Can I simplify that even one more? I'll do it over here. Look at it and just think. Now just think. Can I take a over t out in front? Now what do you notice when I do that? I have tau minus tau rise plus tau rise, or just tau, don't I? Sure. So that's C0. Agreed? All right. What do I do next? Remember, I'm after C of n. I'm not going to get it with integration. What's my next thing I do? Anyone? Take a derivative with respect to time of the original waveform. In doing so, what do I get? This is going to be x prime of t, and it becomes what? The height here would be?
A over tau rise.
Right, a A over tau rise, right? And it stays there until tau rise, and then it goes to?
Zero.
Thank you. And that would be tau rise here. Then it stays 0 until I hit tau, correct? And what happens there? The slope of that line is minus A over tau rise. So now it goes down. It stays there to this point, and this is minus A over tau rise. And this, right here, is A over tau rise. That's the first derivative. That still doesn't get me where I want, does it? My next step is another derivative, right? With respect to time. Here, I get what I want. And this is tau. Now, you're going to have to bear with me because this, I'm running out of board here, so let's see what I can do. Let me go over here and try to get it. When I do that one, what happens at 0? Class?
It goes up to A over tau rise.
Impulse, right? A
Yes.
delta function with a weight, you're right, of A over tau rise, absolutely. Keep going. What happens? Do you all see that? The change, next change is from A over tau rise to 0 at tau rise, another delta function. I'm just going to represent that as a delta function. Minus A over tau rise, and I'm just going to put an arrow. We know it occurs at that time. Agreed, class? Now we keep going on that one. What happens?
Tau, it goes up.
Plus or minus?
Oh, minus.
Minus, right? Make sure you see that. Do you all agree with that? Went from 0 to the, so it's another negative going pulse. This is minus A over tau rise, and it occurs at tau, correct class? This is tau rise. Keep going, next place. At? That's right. Tau plus tau rise, it goes up. This is at tau plus tau rise, and this has A over tau rise. So now we have our series. This is x double prime, right, of t. And we know that series x double prime of t is equal to the summation from n equals minus infinity to infinity of jn omega naught squared times c of n, right? Times e to the j n omega naught, because we took two derivatives of this guy right here. And every time we take a derivative, we bring a j n omega naught out in front, which is equal to a summation here from n equals minus infinity to infinity of c of n double prime e to the j n omega naught t. That this right here is the same as this. You've done the work, you know this is obvious, right class? Now the next thing I have to do is say that my Cn double prime, and I'll do it here, is equal to 1 over t, the integral, it's over any period. That means if the period is from here to here, t, I could go from there to there, but I can see I'd rather go from here to there. I'd rather start back a little ways so I could go through this impulse function. Follow me? I'll start my integration here, and I'll stop at somewhere shy of t. So I'm going to go from, it doesn't matter, just some value minus epsilon plus t to, minus epsilon, pardon me, to minus epsilon plus cap t. And this is going to be of x double prime of t e to the j n omega naught t dt. And that means my C of n double prime is 1 over t. Now, I'm not even going to bother writing the definition of the impulse functions in there. We know what they are, correct class? Everybody with me? So when we do this, the x double prime of t to the j n omega naught t, actually it's a minus sign right there, e to the minus j n omega naught t dt right here. When we do this integration, and we substitute in those impulses, the first impulse occurs at t equals 0, right? It has a weight of A over tau rise. So now I put in A over tau rise here, and I see that it occurs at 0, so I evaluate e to the minus j n omega naught 0 there, right? And e to the j 0 is? 1. 1. So it's times 1. Now we keep going. The next one is that class
Tau rise.
tau rise, and it's got a magnitude of minus A over tau rise. So I'm just going to take this out of here, and I'm going to put 1 minus, and then it would be, I know it turns on at tau rise, so I have to evaluate e to the minus j n omega naught tau rise. So it's minus e to the j n omega naught tau rise. Do we agree with that? Again, I factored out the a over tau rise. Class, do y'all see that? You've got very good eyes if you can see this back there. You do. What's the next thing that happened? I don't even walk over there. Tell me what happens. At what time? What's the next transient? Where?
Tau.
At tau, and its value is?
Negative A over
Minus A
tau.
over tau rise. Got A over tau rise, so it's minus, and it would be e to the minus j n omega naught tau. Correct, class? Y'all, everybody agree? Keep working with me. What's next? Positive or negative? Positive, and it's going to be a plus e to the j minus j and omega naught. Now this is going to be tau plus tau rise, right? Listen to me. If I have e to the j minus j and omega naught quantity tau plus tau rise, is that not e to the minus j and omega naught tau, right? Plus, or times e to the minus j and omega naught tau rise. You follow me on this? So I'm going to just break it that way. I'm going to put a tau here, right? And then make this e to the minus j omega naught, and this would be tau rise. I hope you can appreciate what I'm trying to do is factor it right there. Can you all see that? You know what I've done, don't you? Give me a show of hands if you do. All right? Getting hungry looking at me. Now, when I do this, that's still Cn double prime. I still know I've got to divide that by Jn omega naught squared. Right, class, to get C of n? But right then and there, that is the correct answer. It's not very usable, or we don't know what it looks like intuitively, our computer would. But that's the right answer if we then divide this by what? Jn omega naught squared. Now we get C of n, which means if we divide this whole mess by Jn omega naught squared, we get the right answer. Correct, class? That's still not real obvious what it looks like. I'm going to erase this. I'm going to show you something now. So now I've got my C of n in a form that a computer would understand, but it's not very useful for me. Now, I did this last time. Does anybody remember what I was trying to get that to look like?
Sine and cosine.
Sinc, right? A sine x over x, correct? Because I know what that looks like. And remember I showed you the sinc waveform? That's something I want. So here's what I'm going to do first. I'll put this over here. I'm going to take my C of n, and I'm going to say it's A over tau run. That's tau, is it? Yeah. T, cap T, tau rise. Then it's times, and I'll divide this here by Jn omega naught squared. Then here, look what I'm going to do. I want you to watch this. You see if I factor out, if I just look at this, I have 1 minus e, oh boy, I better write this whole thing. I think I may, not at all. But I'm going to write that whole thing over here. That becomes 1 minus e to the minus j n omega naught tau rise minus e to the minus j n omega naught tau, right?
Yes.
Minus e to the minus j n omega naught tau times e to the minus j n omega naught tau rise.
Shouldn't that be plus?
You're adding that though.
Yeah,
Can't hear.
shouldn't that be plus?
Yes. Sure. That's right. Y'all see that, class? I just rewrote what's over there. Now, what I'm gonna do on here, with these two terms, just listen to me, this term and this term. I'm gonna factor out e to the minus jn omega naught tau, all right? Now just watch this, I'm gonna take this, just focus on this right here. If I have this, it would be 1 minus e to the minus jn omega naught tau rise here. Then, I've got that, hold on. I could do it that way, I'm gonna do this. Now, here, I'm gonna have minus, and watch this, I'm gonna factor out e to the minus jn omega naught tau out of that. That means there's a 1 there, right? And it's going to be plus, no, minus e to the minus jn omega naught tau rise here. Please just take a look at that. I've taken only this part and I've rewritten 1 minus e to the minus jn omega naught tau rise minus e to the minus jn omega naught tau, right? Factor that out, and then from the last part I have to throw a minus sign there, and I'm left with e to the minus jn omega naught tau rise. Do y'all see that, class? Everybody? Now y'all see I can factor 1 minus e to the minus jn omega naught tau rise out of both of those? And that means this part here will become this. It becomes 1 minus e to the minus jn omega naught tau rise here times, when I factor that out, I get simply 1 minus e to the minus jn omega naught tau, don't I? Because this is the same as this. And I factor it. You follow me? Why did I do that? You guys know. Some of you know. Some of you don't want to answer me, but you know. What's the magic? Yes, I'm going to use Euler's, but before I use Euler's, I'm going to pull out what out of these things? I'm going to rip out an e to the minus j and omega naught tau rise over 2, correct? And pull it out in front there, and out of this one, I'm going to pull out an e to the minus j and omega naught tau over 2, correct? And when I do that, I get this. E to the minus j and omega naught, and this is going to be tau rise over 2. E to the minus j n omega naught tau over 2. Now this one will become simply e to the j n omega naught tau rise over 2 minus e to the minus j n omega naught tau rise over 2 times e to the minus or plus j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2. I had to factor these on. By the way, you can add the tau rise plus tau and just put it over 2 right there. You don't have to have 2 separate things. Agreed, class? Y'all remember we did this for the last waveform? Now, what am I going to do with these two guys? This is where somebody says it. Euler's identity, right? Isn't this really 2j sine of that argument? And this is 2j sine of that argument, isn't it, class? Agreed? Are you with me? Y'all understand what I'm saying? Come on, man. Wake up. You guys are engineers. You're the bright boys or girls. E to the j theta, right? Minus e to the minus j theta, right? Over 2j. Isn't that sine theta, correct? Have to know that one. That's high school stuff. Now you have to multiply by 2j. I mean, I got this on in high school. I don't know. It's sort of normal when you do this. You don't like it, but you had it. Right? You had trig, didn't you? You had complex numbers. If you had complex numbers, you had that. Did you have complex numbers in high school or not? Really? You didn't have do you have physics?
Yeah.
No complex numbers. You had physics? You didn't have physics?
Not in high school.
Okay. Well, anyway, wherever you get it, you get it. That's.
Since there's a j squared on the bottom, wouldn't it become cosine?
Where are you looking?
Wouldn't you use the cosine always?
No, these are e to the j theta minus e to the minus j theta, right?
Oh, right.
Cosine is a plus up
Okay,
top.
sorry.
Yeah, are you with me?
Yeah.
Now this is just 2j times sine of that argument. Look at over there. This is 2j sine of that argument. This is just a phase term. So now what I can say is this entire C of n, this is where I'm coming. This C of n is equal to A over cap 2 times tau rise here, divided by j n omega naught squared here. And then I have this phase term, e to the minus j n omega naught. Then it's going to be tau plus tau rise over 2. Then this is going to be 2j times the sine here of n omega naught tau rise over 2 times the sine of n omega naught tau over 2. And this is going to have another 2j, so this gets squared right there. And that's C of n. It's getting close to something we can see. Now, before I continue, can you see you have a 2j squared or j squared times 2 squared? And you got a j squared here, so can I get rid of that for starters? Why not?
I'd say keep, oh wait, actually, never mind.
There's a j squared, there's a j squared, isn't it? I don't want to keep any more than I need to here. So I'm just going to get rid of the j. Agreed? Now, this term right here is a phase. It only has a magnitude of 1. But, I mean, that's an acceptable answer. At least it becomes more and more obvious what it is here. Because I can see these sine waveforms. I know what they look like, don't I? I wanted to put it in terms of a sinc. Can anybody, you know what, the sinc x, we just talked about that with Liz. The sinc, right, of x is equal to what? The sine of x over x, correct? That's the sinc of x. It's the definition of the function, correct? We talked briefly about that. I've asked how many have heard of it. Not many have heard of it. It's a function you'll see over and over again in electrical engineering. It's in a lot of courses. You'll see it over and over again. Now, what I want to do is turn this into a sine x over x kind of deal. Well, that means my x that I need is n omega naught tau rise over 2. I look over here, I surely have n omega naught, right? I have a tau rise, don't I? Matter of fact, what I can say is make this n omega naught right here so you can see what I'm up to. Now, look, I need an n omega naught tau rise over 2. I have tau rise n omega naught. I need over 2. I got 2 squared there, so I'll just divide this one. I'll put a tau rise here, and I'll divide it by 2. And when I do that, I get rid of this. Are you with me? Now I've got this argument down there. Follow me, guys? Next one I need is n omega naught tau over 2. Well, there's an n omega naught, and now I put in a tau downstairs, or in the denominator, which means I have to put one in the numerator, correct? But now I need this divided by 2, and looky here, I've got it. Divide top and bottom by 2. I get a 1 there. And now this is divided by 2, is it not? This is really useful too. This is the way we do engineering stuff. So we can see this whole thing is going to come down to what? A times tau over t, or the duty cycle, right? Then it's going to have the phase term, e to the minus j n omega naught tau rise plus tau over 2. And then we got a couple of sinc waveforms. This divided by that is sinc of that. So it's times the sinc of n omega naught tau rise over 2. Then the next one, sinc of n omega naught tau over 2. And both of these waveforms are well-established waveforms that we've talked about briefly and that you'll see over and over again. And that is the value of C of n. And it's very easy to calculate a value because here, in terms of the magnitude, can you see if you want the magnitude of this? It would be the magnitude of that, which is just a tau over 2, correct? Or a tau over t, correct, class? Because this phase term has a magnitude of 1. Are you with me? So the magnitude of C of n is A times the duty cycle there. Then over here, when I'm evaluating this, I'm sine of what? It's an angle, right? So pick a value of n. We can get the rest of this very easily. The sinc function, do your calculators have sinc on it? I think they do. I think so. I'm almost positive any engineering calculator will have sinc. They also have hyperbolic tan, hyperbolic sine, and hyperbolic cosine. What's that? Doesn't yours have it? Surely it does. S-I-N-C. See it? That's the hyperbolic sign. No, S-I-N-C. I don't know what else, you don't, don't you have those little function buttons you hit for higher order functions? Well, you look it up, I'm almost positive it's on there.
It should be
It's
a
on-
catalog, if anything.
If it's on my old HP from 1989, then it should be on yours.
Yeah, I don't see sync, I see sign H.
No, that's the hyperbolic sign.
Catalog has it all.
That's 6.
I'm in catalog.
All right, well, if I'm wrong about this, I apologize. It's a very common function in engineering. We use it all the time. Anyway, that's what these two are, and it's very, very easy to identify. You can always put sine x over x if you want, where x would be that argument. So that's how you do that, bro. I need to get on with some other things today. I hope I answered your question, whoever asked it. That's the entirety of it. And you're probably thinking, well, is this something we should know for the exam? Yeah. I mean, this is something you should know this. You're going to work with it because this is a very obvious one. It's not even a hard one. This is very obvious. 2 derivatives and you get delta functions. From there you can get C of n. All right. In any form, I mean, I'm not going to ask you to put it in every form possible, but some simple things I'll ask you about that. Now, next thing. The next. We've done Fourier series analysis, and last time I was talking about why it was important and how we took everything we put it in terms of a cosine series. Y'all recall that? How many do? So I'm just going to say for any periodic waveform, we can represent it as an input x of t as C0 plus, then it's a single-sided summation from n equals 1 to infinity of 2 times the magnitude of C of n times the cosine of n omega naught t plus the phase angle of C of n, right? And I said that these terms, term by term, look like magnitude times cosine of omega naught t plus a phase angle, correct? And each one of those is easily translated into a phasor where you have the magnitude, which would be 2C of n, at the angle C of n. It would be like 10 volts at 30 degrees, driving an RC network where you want the voltage across the capacitor. What would you do? You would take 10 at an angle of 30 degrees, multiply it by what? The transfer function, right? Or the impedance of the capacitor over the impedance of the capacitor plus the resistor to get the output voltage. Do you with me with this? Then you would have a magnitude at an angle, and then you would turn it back into a cosine series by taking the magnitude of that voltage, and then you would times it by cosine of n omega naught t plus the phase angle of that voltage. Now, I'm going to do this to you step. Y'all, you remember we doing this on Friday, guys? You know how to get C of n, period. So now we can say, if we go to the phasor domain, we can say x phasor here would be C0, then it's plus the summation of this from n equals 1 to infinity, now in the phasor domain, of just 2 times magnitude of C of n at the phase angle of C of n. Each one of those looks like an individual voltage at a given frequency n omega naught. Are you with me? Are you with me, class? Now, take any circuit you want. That's the input. Any circuit at all. Here comes the input, my x phasor. I'm just putting a tilde to indicate phasor. It goes in. You've got a circuit. The circuit has a ratio of output to input known as a transfer function. It's some h of really of n omega naught, because it's at the frequency n omega naught, right? Each one of those is at a frequency that has to do with n, but not just n, but it's times omega naught, right? Times the fundamental, yes, miss.
Is that a cosine or is it a sin?
This is a cosine.
Okay.
It's standard phasor form. Cosine of a frequency times time plus a phase angle. Just like you did in circuits, it's basic. Nothing complicated. That goes in, now my output that comes out, Y phasor, is simply going to be X phasor times H of n omega naught. Agreed? Now that H of n omega naught is the complex number. It has both magnitude and angle, right? But at the end of the day, I can say this can be expressed as the magnitude of X phasor times the magnitude of H of n omega naught at the angle of X phasor, really angle of X phasor, plus the angle, it's really the angle of X phasor plus the angle, really plus the angle associated with H of n omega naught. Now that would be the output in the phasor domain, right? That's for anyone for any n value. If you want the total output, you would have to sum these for all values, correct? So I'll put it over here. That's the input. Now we'd say the output in the phasor domain would be equal to that'd be the summation, well actually it would be C0 here times H0 plus, and then it would be a summation here from n equals 1 to infinity of the magnitude of X phasor times magnitude of H of n omega naught at an angle, each one of these at an angle of X phasor, whatever that angle is, plus H, really H of n omega naught. And now you've got the output in terms of values at specific frequencies at n omega naught, but you're summing them all up. Now what do you do if you want to go to the time domain with a phasor? Let me put it to you this way. If I like to do it 10 at an angle of 30 degrees in the phasor domain, I want to go to the time domain, what do I do? Anyone?
Cosine.
Well, first magnitude.
Sorry.
Magnitude 10, right?
10.
Times cosine of
Omega naught t plus.
omega naught t plus the phase angle of, or really plus 30 degrees, right?
Yeah.
30 degrees is the phase angle. Are you with me? Now we don't have just omega naught, we have n omega naught. Right? So now what our output's going to look like? That's complex. That's a phasor domain output. But now in the, yes sir?
Is that H and omega naught? Is there a phasor?
This is
above
all,
that?
this is the angle associated with these two.
Okay, so there's not the tilde over the H?
Well, you don't need it really. It's really, this assumes the angle associated with this and this. That's what I mean with this. It's the angle of those two. And it's additive. So now I'm going to put the whole thing in terms of the output. Are you ready? I'm going to erase this. This is the thing. So now if we have this input from any periodic waveform, we can feed it into any linear time invariant circuit made of resistors, capacitors, inductors, op amps, everything that is as long as it's a linear time invariant system. And we can get y of t, this is the bottom line on this. The output would be equal to C0 times H0. That's the transfer function evaluated at 0, plus the summation n equals 1 to infinity of 2 times the magnitude of C of n times the magnitude of H of n omega naught times the cosine of n omega naught t plus the phase angle associated with C of n plus the phase angle associated with H of n omega naught. And that's it. That's the output. Now, you can't do this in your head. but you can do it on a computer like that. And that's what programs like, have you used P-Splice or LT-Splice or any of these programs?
LT.
That's what they do. You can have any arbitrary waveform, and they use this. They do. I'm gonna give you problems like this. This is the one time I actually do a collection of homework. And it's a bonus. If you hand it in, it's added onto your quiz grade. It's weighted the same as a quiz, it's added on. And, but it has to be done right, it has to be a good job. You hand in a piece of paper. If you don't do the MATLAB, and you don't do the printout, you get 0. Now, people will collectively work on this, I'm aware of it. I mean, if I see an absolute copy, you both get 0, so I'm just gonna tell you that. But I expect if you do it, you'll be rewarded. Try it on your own. And I'll give you sort of a template code that you can modify. I know some of you, how many are familiar with MATLAB? All right, I'm gonna tell you one thing about MATLAB. I don't think I got 148 my time, or 140, I hope that's right. Is it close?
Yeah.
I think I told you before, students hate MATLAB at first, because there's a learning curve. Everywhere I go, that is the #1, that and Python are used to do the prototype. That's the first codes. The preliminary codes, when they're modifying, changing, getting everything right, they're easy to use. MATLAB is a godsend. When you go out in the world and you want to make money, real money, and you got to do stuff, Python and MATLAB is the way it's done. And the prototyping, when they actually get codes, high-speed codes for operation, they take these higher level languages and they port them into C++, I mean, really object-oriented Fortran 90 or C++, so they can move really fast, and then you get this guy here can tell you all about it. But basically what you get is a lot of codes done in parallel, and you get like graphical processing units. Do you do CUDA card stuff over there, Jim? Right, no? You can do stuff so fast and seamlessly. Once you get the base code working, it breaks it up that everything can be done in parallel, and then assembled into a serial part, and then in parallel again. And it's amazing how fast they are. These gamers, anybody here a gamer? Who is? You know GPUs? All cards? Those are the things gamers should know and appreciate. They're doing things so fast that maybe 15, 20 years ago, a mainframe would be neat to what you do on a gaming site now. I mean, I'm not a gamer, but I know about these graphic cards. And that's what I used to do some of my work. The high-speed graphic cards, programming and stuff. All right, I'm out of time with this one. Where we're going next, we're done with Fourier series. We're going to Fourier transforms. I'm going to give you a problem related to this, to do with MATLAB, all right? I'm going to also give you some preliminary stuff with the Fourier transform because they're trivial if you know Laplace transforms. Laplace transforms, in a nutshell, are Fourier, only with sigma set to 0. And don't miss tomorrow in the next lecture. It's very, very important.